Good morning, Dasha. Good morning, Kayla. Okay, so let's get started with the material for today. I hope everybody is having a good day so far. Does anybody have any questions for me before we get started with the new material? About 2.1. Okay, so I think we are on, actually, I might have put the wrong title on this lecture. I'll have to fix it, but today is for section 2.2, and then we're also going to be having a class activity. So hold on for 1 minute. Let's see if anybody else jumps in here, and then we'll get started with the material. Okay. I'm going to go over to my camera. This is these are the pages, or let's see, I think there are 2 pages from the lessons note packet, and I'm going to do those problems from both pages, and then we're going to do a class activity that reviews both of the sections that I've covered thus far. In chapter 2, just to give you an overview, there are only 5 sections. I think sections 2, 3, and 2, 4 are the harder ones, just because they're all about conversions. But, I'll go through those with you slowly, as I am on all the material. And you can ask whatever questions you want if you do get stuck. And I'm just going to make sure that you know how to convert from one unit to another and from one system to another. Like, for instance, we use numbers in the English system, and you know that other countries use them in the metric system. So we'll even be converting between systems and converting within the same system. We'll be doing both kinds of problems. I just wanted to remind you once again that if you are trying to follow with me and have an outline that you can just fill in, this is where I'm getting this from, what I'm going to be working on right now. Let's see if I can share with you. Okay, so here we are in your shell. This is where I'm getting this from. I just pull that up, and then I go to the sections that I know I'm going to speak to you about. And usually it's only 1 or 2 pages. So I just print those 1 or 2 pages, and that's where I am filling out the notes from. Those are outlines for the lecture. So those are good, because if you have that in front of you, section 2.1, there's no way that you wouldn't be able to do well on the end of class activities. I only mention this because there are a few people that are not doing that well. In addition to being able to look at your notes while you're doing the class activity, I'll try to put you in groups, and of course you can also ask me right in the middle of doing it. You can just call out to me and say that you're stuck on a particular problem, and I will help you through it. So it's very easy to do well on that end of class activity if you just take my suggestions. Okay, let's move back over to the document camera. So I can demonstrate some problems for you. So just to give you a little rundown before I actually start solving equations, that's what this section is about. This is section 2.2. There's certain terminology that I'm going to be using as I try to explain what I'm doing. And so that you can follow what I'm saying, you need to know what the words are that I'm using. So that we're going to start by defining some of the vocabulary that is related to equations. Okay, so the first thing that we're filling in, we have some definition to fill in. A letter that is used to represent a number. That's called a variable, because it can take on many different values depending on what you plug in for it. So any letter that represents a number. We can use the letter X, we can use the letter A, we can use capital letters if we want, etc. Just any letter that represents a number. Okay, next definition, a number that's in front of a variable. That's called a coefficient. Okay, an example of that would be something like this, where the 3 represents what I just defined. The number in front of the variable is called the coefficient. So that 3 would be the coefficient. Okay, moving to the next definition. A combination is variables and constants using mathematical operations and grouping symbols. That's called an expression, an algebraic expression. I'll just put that out here. Algebraic expression. Okay, it's an expression made out of coefficients, variables, mathematical operation symbols like plus, minus, things that mean multiplication like that, or a dot. I'll try not to use X because I might use X for a variable, or division signs. There's different ways to write division also. So this would be an example of something like that. Something like 2x. I'll try to throw in a little bit of everything that was just mentioned in that definition. So you see, we have variables, variable x. We have operation symbols, mathematical operation symbols, minuses and pluses. And we have grouping symbols. Grouping symbols being the parentheses that I've used. So that's an example of an algebraic expression. The minute that you throw an equal sign and there's things on the other side, then it goes from being called an expression to an equation. So a statement or an expression, two expressions that are equal, here they define it as a statement that two quantities are equal. That is built using expressions and equals. So for instance, if I wanted to have, something like this. So we're defining the word equation. And then I'll give you an example of it, which is 3x minus 9 is equal to 4 times x plus 1. So I have an expression over here, an expression over here, and there's an equal sign between that joins the left side to the right side. So you have two distinct sides. That's called an equation. You're going to be mostly in this section solving those equations. So let's see what else. The next one is an equation with multiple variables that is used to calculate some quantity that we are looking for. And that would be called a formula. Like for instance, you guys have studied simple interest and compound interest. This was the compound interest formula, which, by the way, I think it's used in the activity today. I keep bringing it up because students just tend to be, for some reason, baffled by how to use the power key. So I just keep bringing that up so you can keep practicing on it until the point where you are more confident. So this would be a formula. See how there are several different variables here? And it's an equation. And it helps you to calculate some quantity that you're looking for. In this case, it would be the final amount in your compounded interest amount. That's what that A stands for. This is principal, the original amount, the rate as a decimal, T for time. That was in in chapter 1. And then we have these kind of problems. Typically, when you're in an algebra class, they will ask you whether or not you understand the difference between independent and dependent variables. So whenever you use this word or this word, you're talking about the variables that are in the expression or in the equation. When you're talking about the actual values, the actual numbers, let me say it two different ways, then we refer to them as input value or an output value. The input value is associated with the independent variable, and the output value, the actual number itself, and they can change, that's why I put an S on it. It doesn't have to just be one value. What you are inputting in for the variable, that's called the independent variable. So the word input is with respect to the actual number that you're going to plug in for this variable. And the output value, what we also call the answer to the problem, the output value has to do with the answer that you get for the dependent variable. But they like to ask these questions in your book as well as in Alex with worded problems that are in the form of a type, almost, like a sentence. It's not a full sentence, that's why it doesn't have a period. But they like to ask worded problems like this and see if you can understand what is dependent on what. What is the independent variable and what is the dependent variable? And a lot of students like to take these and write them as equations. Because when you're doing an equation, the variable that's by itself, the one that's by itself is called the dependent variable. And the answer you get for is called the output value. So like, for instance, let me give you an example right here. Let's say you had something like this. This is an equation that we will study in detail in Chapter 3. We will learn all different things about it, the slope, the y-intercept, how to graph it, how to graph two of them at a time, how to find a solution set for two of them at a time, and how to evaluate these. So this kind of equation, you see you have two different variables. The one that is by itself is always called the dependent. Remember, I use this word when I'm talking about the variable itself. So the y that you're seeing right there is the dependent variable. The value that you're going to end up getting for y is called the output value. Okay, so output associated with the dependent variable. Then we also have this right here. So this variable right there is it's called the dependent variable, and the answer, the value that you end up getting for it, is the output value. Now you're not going to get anything for it unless you plug something right in for x. So where you are going to put your value in, that is called the input value that you're going to put in there. It is also happens to be called, if you're talking about this particular variable right here, that is called the independent variable. Oops, forgot the E. Okay, so this is called the independent variable. And the value that we plug in right here is called the input value. Okay, maybe that'll be easy for you to remember, although you could put it on your note card if you want to. Both of these start with an I. Maybe that would be a way of you remembering it. So independent variable, the value that you're plugging in for that variable is called the input value. Okay. All right, so moving on and trying to maybe create equations just like I had right here, and maybe it'll be easier for you to get these correct because students have a problem with this, which is what I tend to pull out of the material for each section so that we can concentrate on that kind of stuff. Okay, so like for instance, let's say I wanted to make an equation out of this scenario. You have the height of a tree, and maybe I'll represent that using the variable h, and you have the age. And let's say we're talking age in years. So I'll use A for age. Now you can use all lowercase letters, capital letters, a mixture. If you want to call this just big H, you can. Lowercase or capital allowed. And if I wanted to make an equation out of this, let's say I told you I have a tree in my yard. And the height of that tree grows 3 years, grows 3 feet with every year. So every year that passes, the tree gets another 3 feet taller. So the height is really based on the age of the tree because every year it grows 3 feet higher. So if I wanted to make an equation out of this, I could say the height of the tree is going to be equal to 3 feet. I'm not going to squeeze the units in there. 3 feet times the age of the tree. And let's say age, this A right here stands for years. So when A is 1, if you put a 1 in there, that means that the tree is 1 year old. If you put a 2 in there, that means that the tree is 2 years old. So I'll come over here and I'll define this. A is the age in years of the tree. Just so you know what each thing stands for. And H stands for the height of the tree after a certain number of years. See, sometimes if you can write this worded expression as an equation, then it's easy to tell which one is the dependent and the independent variable. And they're asking you that. Which one's the independent versus the dependent? And I had told you that the dependent variable is the one that's by itself always. So this is the dependent variable, and this one is the independent variable. So there's going to be tests like questions like that on the test. Okay, we'll put the dependent in yellow, just like I did over here, and this is your independent variable. Okay, moving on to the next one, and we'll try to do the same thing. And try to take this worded expression and turn it into an equation. Okay, so let's see. This time we're talking about a score on a test and the amount of time spent studying. So why don't we use, I'm going to use big S for the score on your test, and I'm going to use time spent studying. So let's say that time is in hours. I'm going to come over here and define what each thing is. Score on the test, I'm just getting this right from the words. It's the score on the test. And then the little t that I'm using to represent the word time, that's, let's say, the amount of time spent studying in hours. So I could write a little equation. Your score on the test is going to be equal to, and let me throw a number in here. Let's say that your score goes 10 points higher. I'm throwing in my own coefficient. I'm making it up. Goes 10 points higher every time you study for an hour. T represents time in hours. So if you study for 1 hour, you would get 10 points. 2 hours, you'd get up to 20 points. 3 hours, you would get up to 30 points. So this right here would be the dependent variable, the one that's by itself, and the one that has an operation going on this side. And sometimes there's several things going on here. Here there's multiplication. This would be called the independent variable. Now you don't have to write them as equations in order to figure this out. I think, if you have good enough common sense, you know that your score depends on how much time on the amount of time you spend studying. So another way you could do these problems is you could try to insert the word depends somewhere in the sentence and see if it makes sense. Understanding that the two main things here are score and time studying. You could try saying the score depends on time, or does time depend on your score? Time does not depend on people's scores. It's the other way around. So you can try and insert the word depends, but it's kind of an abstract type of thing to answer these type of questions. That's why students struggle with them. So either way, you can make a little equation here. You could say hours worked. Oops. Let me label them first, and then I'll write the equation. So I can use H for hours and P for paycheck. So let's say that I say your paycheck is equal to, and let's say you make $9 times each hour. And that would be a little equation. Your pay depends on how many hours you work. So this is the dependent variable. This is the independent variable. Okay, again, I'll put this in yellow for the dependent variable. And my independent variable is the one over here. Again, you don't have to write them as equations. You can just try inserting the word depends. Your paycheck depends on the number of hours you work. So if this depends on that, this is the dependent variable. Okay, moving to the actual calculational problems. Okay, first page in this section in the notes is just really vocabulary and trying to understand in a worded situation what is dependent on what. And then we come to these equations. And so I've selected several types of equations for you at varying levels of difficulty, and I'm going to go through each one. First of all, you should know that when you're solving an equation, you are finding the one number, because you notice that all of these equations are first degree. And if you don't know what that is, let me refresh your memory. The power on the variable here, when you don't see one, is said to be an x. And whenever the power on a variable is x, we say that it is first degree. And that means there will be one and only one solution if there is one at all. Because some of these equations don't have solutions. I'll show you what to look out for in that case. Okay, so only one solution because it's first degree. Notice that everything here, that the x's are no higher than first degree because they have no powers, they're first degree. So if the highest power on any variable happens to be first degree, that means you're only going to have one solution. Likewise here, likewise here. These are all x to the first degree. And no, when you put these problems where you're collecting like terms. Okay, so let's start with this one. This is the easiest one. And again, in general, you got to know where you're headed when you solve an equation. The whole idea when you solve an equation is to isolate the variable. There should only be a variable in one place, and if there isn't, you're going to collect like terms together. Okay, so you're going to isolate the variable, and the way you're going to do that is by performing inverse operations. And I'll tell you what I mean by that. Okay, if you don't know what inverse means, it means opposite operation of. Like for instance, if you see a plus sign, the opposite of that would be minus. If you see a minus, the opposite of that would be plus. So these are said to be inverse operations. If you see multiplication, the opposite of that is Let me not use an x just so you won't think it's the variable x. Got to be careful with that. So if you see multiplication, anything that indicates multiplication, and we can do that, means multiplication or parentheses. Opposite of that, inverse of that is division. So you have to know your inverse operations because you're going to be trying to move terms around. And the way you get terms to cancel or move around is by performing inverse operations. Like for instance, I know I want to isolate this x. Right now, what's keeping it from being isolated, in other words, all by itself with no number in front of it and no number added to it. So you can see that those are the things that are hovering around the x. It's being multiplied by 3. It's got a coefficient of 3, and 2 is being added to it. That's a positive 2. So I want to remove all of these things. Please hear what I'm saying, that this coefficient will always be removed as your very last step. Otherwise, you introduce fractions into the problem way earlier than you need to. Not that you're not allowed to get a fraction for an answer, because you can. But why introduce it at the beginning of the problem only so it can make the rest of the steps harder? So this will always be removed last. Anything that's added or subtracted, you are going to move it to the other side and make it cancel on this side by performing the inverse operation. So since this 2 is being added, you could also just look at the sign right here. Look at the sign in front of it. It's a positive 2. Opposite of that is, let me get rid of all these marks so you can concentrate. Opposite of this is minus 2. Now, because this is an equation, that means it is balanced on both sides. What you have on each is equivalent. It's like a balance beam where you have, or like a scale, where you have 5 pounds of gold on one side and 5 pounds of gold on the other side. It's balanced at that point. If you take a pound away from one side and you want it to remain balanced, you have to take a pound away from the other side. So that's exactly what this is like, a balanced scale. So whatever you do to one side, in order to keep this balanced, you must do the same thing to the other side. Always, same operation. Your goal is that you are trying to isolate the x, get it by itself. So right now we are stripping this 2 away, leaving us with just 3x and a 12 right here. If you want to, you can put a line right here so to show what the equation has now transformed into. I usually do that. I do my step on both sides and then I put the line just to kind of help me focus. Now then, when you go into the next step, this is called a 2-step equation because I just did 1 step right here. Now you're going to remove the 3. So you have to look at, when you're asking yourself, how do I remove something? Like here, when I tried to remove the 2, I looked that it was positive, and that made me do the opposite of a positive, or inverse of a positive, which is to subtract 2, or to use a negative 2, because they mean the same thing, subtract 2 minus 2. Or negative 2. Here, I want to look at the fact that this 3 is attached to the x by way of multiplication. Whenever there's a number right up against an x, that means they're being multiplied. When you read this out loud, it is read 3 times x. So to remove the 3, you do the opposite operation of multiplication, which is division. To keep both sides balanced, you have to do the same operation over here. These will cancel, leaving your x nice and isolated while giving you a 4 on the other side. Now, if you want to check your work, so we think this is the solution, if we didn't make any mistakes. If you want to check and see that it's right, you should know how to check your solution. You check any solution copying the original equation, 2 plus 3x is equal to 14, and leaving a blank spot where the x is. Then you plug in your supposed solution, and if you get the same number, same sign, same number on both sides, that means that this is correct. So this is 2 plus 12. You can already see that you are getting a true statement. You have a 14 on one side and a 14 on the other side. that means that this answer is correct. Do not give that as the answer. This is a proof that that answer is correct. And you may be asked in Alex to do a check on your solutions. Okay, next problem that you see down there, feel free to jump in and ask me whatever it is that you're concerned about or don't understand. Okay, here, I mean, you could do this in 2 steps, but why do 2 steps when you can do 1 step? I mean, you could look at this as, okay, this 5x is being divided by 4. I'm going to multiply by 4 to get rid of the 4. But then you'd still have the 5 to get rid of. And I'm going to move this down here because that 2's in the way. You actually can get rid of the 5 and the 4. And when there's an x in the top, yes, you can scoot it out to the side. Do not drop it down into the bottom because then that means something else. Okay. So when in the case of a fraction as a coefficient, a fractional coefficient, remember a coefficient's a number out in front of x, you can actually get rid of the whole fraction just by multiplying by what's called the reciprocal. Reciprocal just means take the fraction that you're looking at and flip it over. And probably most of you know that. Don't forget that whatever you decide to do to one side, I've just decided to multiply by 4/5, you must do it on the other side as well, so that you're keeping both sides balanced. This is going to cancel, leaving you with x. And then this side, if you don't want to get into a situation where you're having to put that in the calculator, it's really not necessary. 5 is the same thing as 5/1. When it comes to fractions, if you have matching numbers in the numerator and denominator, top and bottom, they cancel, leaving you with just 4/1. Because what you do is you take what's left over, make a fraction, or you can just write it as 4. Okay, and that is the answer. Just happen to get the same answer again. If you do want to check it, you can just take your original equation, 5/4 x, leave a blank spot for x. Supposedly that's supposed to be equal to 5, and this is possibly your answer. We're about to prove it. So I just plugged in the 4 into the original equation. 4 is the same thing as 4/1. We have the same number top and bottom, and we also have just a 5 left on this side and a 5 on the right side. Getting a true statement, in other words, the same number on both sides when you're checking, means that this answer is correct. Okay, moving to number 3. I was saying that before you start doing things to each side, to both sides, where you decide what you're going to do and you do the same thing on both sides, you should have your x's all on one side. So if, or all together, combined, excuse me, wrong word. You should have them all combined. So if you see that on this one side, you have x's here and x's here, you want to combine those into one term. So when you're combining like terms, this was on the last test, these are both x to the first degree, so you just use these coefficients out front, that gives you 5x. Now begin to solve. All you did right there is clean up those two terms. You weren't really moving things from side to side, and students that are very shaky with regard to solving equations, you'll typically see them when they try to do this step thinking that they're adding 2x and then you see them adding 2x over here. You're not trying to do that. You're just trying to rewrite this as one term to make the problem simpler. You're not doing the steps yet where you're moving things from side to side. Now I'm about to do that. I'm about to do my very first step where whatever I do to this side in an effort to isolate the x. See, here I wasn't trying to isolate the x. I was just trying to combine like terms. Now I'm going to try and strip away that coefficient. So I'm going to try to isolate the x by doing this one step. Whatever I do to this side, I must do to the right side. So these cancel, leaving the x all by itself like we want to happen when we're solving, and over here getting a 1. And if you are going to check that, you can just copy the original equation. And I know it would be easier to just write 5x, but you never know at what point you might make a mistake, and that's why they suggest that you actually copy the exact original equation as it was. Now dump in the number that you got, and we're about to see whether 1 truly is a solution. So we have 3 plus 2 is 5. That was, I guess I should write that. I get 3 up here, get a 2 right here, you get a 5 on both sides. So that means this was correct. Okay, moving to top of the page, and we have number 4. So there's no x's to combine here. No, I like to clean up either side before I start moving things from side to side. So this step that I was telling you to do right here, combine those x's, that's like cleaning house on the left-hand side. You're tidying up a bit. I wasn't really doing anything where I did it to both sides until I got to this step, dividing by 5. Okay, let's see. I don't have any x's to combine, no x's to combine there. Okay, so I'm ready to start moving things from side to side. Now I do see that there's x's on 2 different sides. And if I want to be able to do what I did here, combine like terms, they have to be on the same side. So you can either move this negative 8x over here, or you can move the 7x over here. Now, I don't really like to disturb my positive terms because I like to have as much positivity as possible. So I think I'm going to take this negative 8x and move it over here. You should always be looking at the sign in front of the term that you're moving. Like when I did this first problem, I know that you're very apt to look at that sign right there. But what if that would have been a minus and this was a positive? It might cause you to do the right thing by looking to the right of the number. Look in front of it, because that's really what determines what you're going to do to both sides if you're trying to move that number. It wasn't so much about that, because that could have been a minus, and I still would have done this. It's that this was a positive, and that's why I used a -2, or you could call it subtracting 2, but it was really all about the sign that was in front of this. Likewise here, it becomes very evident here. See, this really proves my case. It's not about that guy right there. It's about the number in front of it. If I want to make this go away, the opposite of -8 is +8. And I'm talking x's. The opposite of -8x is +8x. It's the same thing as adding 8x. Whatever I do here, I have to also do here. So this is going to cancel with this. I'm going to get a 26. 7 and 8 is 15x. Then subtract 4. All I did was drop the -4 down. Okay, now I'm going to continue trying to isolate the x. Remember I said the coefficient should always be dealt with as your very last step. So it's the -4 that I'm going to get rid of. You can call that -4, you can call it -4. But always be looking at the sign in front of the number, because that determines what you're going to need to make it go away, to make it move to the other side. So I'm going to add 4 here, and therefore I'm going to add 4 here. That'll give me the 4's canceling on the left and just having a 15x on the left while having a 30 on the right. And I'm going to divide by 15 here as well as here, giving x equal to 2. And if you want to check whether that's right, you can just go 7x minus 4 is equal to -8x plus 26. I got to scrunch that in there. Supposedly my answer is 2. I'm going to find out if that's correct. 7 times 2 is 14. 14 take away 4 is 10. So I better get a 10 on the other side, or else I know this is wrong because I did some kind of step incorrectly. Okay, let's check it out. Negative 8 times 2 is negative 16, and then there was a plus 26 on this side. All I did was copy that original equation, and I put my supposed solution in there. This plus this is 10. So since I got a true statement here, that means that's correct. Okay, moving to this next one. Now here you have two fractions. So the way you could handle this is just cross multiplying. That'll get you the answer there. If you want to get rid of two fractions at one time, like here in this problem, I don't know where it was, this one, I just wanted to get rid of that one fraction in front of the x. So my technique was just to multiply by the reciprocal. That's what, when you flip a fraction over, that's called the reciprocal. That's the mathematical name for it. This is the street term. We're just flipping it over. But when you're faced with a fraction on either side, I think the best way would be to, you could cross multiply, but you could also do this. If you want to think of this, let's see, I'm trying to think of the way that we'll be able to do it in the least amount of steps. I think this would probably be even better. You could look at this side right here as x being divided by 14. And you want the 14 out of there because the idea in every single one of these solving problems is to get the x by itself. So I want this gone. So if what's happening to the x right now with respect to this 14 is that it's being divided by 14, you could just multiply by 14. And multiply by 14 over here. Let me write it more clearly over here. So I am multiplying both sides by 14. I'm just going to write it down here again so it's clear. Okay, so what I've created now is I've allowed this 14 to cancel. I made sure to do the same thing to both sides, multiply by 14. So now I have just the x. I've isolated the x. And then the way you could handle this is 14 over 1. When you're multiplying a fraction times another fraction, you're supposed to multiply. So 14 times, you multiply the tops. Let me say that more clearly. You multiply the tops and you multiply the bottoms. Oh my God, I can't put this in. Okay, so 14 times 5 is 70. And then 1 times 7 is 7. So multiplying the tops, you got a 70. Multiplying the bottoms, you got a 7. 70 divided by 7, 10. And there's other ways to deal with this. You could reduce this way, reduce that way if you want to. I think this is the easiest way, but it's up to your tastes. Okay, so the answer is supposedly 10. If you do check it, I'm just going over the checking with you. I don't know if they require you to check in Alex or not, just so you're refreshed with regard to how to do it. You copy the original problem, 5/7 is equal to x over 14, leaving a blank spot where wherever the x's are, and then putting in what you believe to be the solution and seeing if you get a true statement. Here, all you would do is reduce. 2 goes into the top and into the bottom. And the minute that you reduce, you have 5/7 on the right as well as 5/7 on the left. That means this is correct. Hold on for 1 second. Okay. So last problem, we're going to be evaluating. Evaluating means that you may have an expression or an actual formula, and you're just plugging in different values and trying to observe order of operations. Please excuse my dear Aunt Sally. You may remember this. It tells you in what order to perform your operations when you have a problem that has several operations in it. Okay, you could have something that has exponents, multiplication, addition, and subtraction. So this is what you're always supposed to do first. You're supposed to look inside the parentheses to see if there's an operation inside the parenthesis where you can put two numbers together. So this has first priority. This has second priority, doing any and all of the exponents. These two have equal priority. So you're going to pass through the expression left to right. And if you hit multiplication first, you'll do that first. And if you hit division next, you'll do that. But you're going to do all multiplication and division in the same pass as you go from left to right. And you will not do any addition or subtraction until you have finished up all the multiplication and division. The last thing you're going to do, so fourth priority, is addition and subtraction. That's what please excuse my dear Aunt Sally means, or PEMDAS, however you want to remember it. Okay, coming to the problem, it's 3x. I'm going to copy it down here, leaving blank spots where the variables are, minus 4 times y, minus 8. I left blank spots where the x and the y was, just so I can plug in the values that they've asked me to plug in. You're going to plug in a 2 for x and a 3 for y, and then you're going to observe PEMDAS. Okay, I see here that the operations that are apparent in this problem are multiplication there, multiplication in the middle, and then there are subtractions. You never do any addition or subtraction until the end. So all multiplications have to be done first. So I'd get a 6 here. I'd get a 12 here. Now bring down the minus signs. Now do the subtraction. So you're obeying this order of operations. Put two numbers together at a time, or put all three in your calculator. I say 2 at a time just because I do it in my head, but you can just put all 3 of them in there if you want to. Just go 6 minus 12 minus 8. Okay, negative 14. Okay, that concludes the notes. We're going to do an activity now. This will be part of your participation grade. It's going to cover 2-1 and 2-2. Please wait a moment while I open up the Socrative activity where you're going to find the problems. I'll tell you when to go in. You can go to the website if you want to, but let me get there first and open up the classroom because it's not opened up yet. Okay, you can get in there now. Don't forget that after you go to Socrative.com, please put your last name, comma, your first name. Give me both names, please. And when you try to get into my classroom, the name of my classroom is Zeiss. Okay, everybody go over to the activity and complete that activity. Please feel free to reach out to me and ask any question that you want. I'm standing by listening to see if you ask a question. And I would prefer if you just say it out loud if you would, because I can't see the chat box from here. Although I'll check it if I see the beeping noise. Brooklyn Graves, can you hear me?
Yes.
Okay, you saw that I fixed your grade in the grade book, right?
I haven't looked yet.
I have no idea why when you made that comment in the chat box, I went and checked it right away after class. I have no idea why that grade went in there because the grades filter automatically from Alex into the Blackboard gradebook. And when I went to check your grade in Alex, I saw what you were talking about, so I re-entered it.
Okay, thank you.
Yeah, you're welcome.